session, the last talk of the week. Sijue Wu from Ann Arbor, who is going to talk about time-dependent waves as well. Today it's about water waves with angled crests. Please.
Okay, thank you very much. I'd like to thank organizers for the invitation to this program. It's a very nice campus. I've been here before, and I'm just happy to be here for the fourth time and enjoy so far. Okay, and what I'm going to talk about is the title. Okay, so the question is the following. So this is like, say, in the middle of the ocean, right? And certain waveforms, and then you want to understand, say, what is the subsequent motion? Okay, so you can ask yourself a lot of questions. For example, what's the subsequent motion, or what are some typical behaviors in the middle of the ocean? Okay, so here we are going to assume there's no wind. So this means we assume the density of the air is 0, okay, no wind. And we will also assume that there's no surface tension, okay? And we assume that there's a gravity, okay? So we assume that air density is 0, so no wind, and the water density is just 1, okay? And the water region is in general below the air region, but there could be overturning wave like that. And we assume this is the fluid is inviscid, incompressible, and irrotational. So we are in the middle of the ocean, and in such open field, we know that, well, the fluid is approximately inviscid and incompressible, so it's quite reasonable to assume that. Okay, and irrotational indeed is an extra assumption. But we do know that, okay, so here I'm also assuming that there's no bottom. Okay, so this means really there's no boundary. So we know that, well, for the fluid oil equation, we know if it's initially irrotational, it will remain irrotational for all time. So this is valid for all time if it's valid initially. And we also assume the surface tension is 0. So again, we are in the middle of the ocean. We know that surface tension is responsible for ripples, right? And we just care about the motion of the large wave. So we can just safely neglect surface tension here, and this is the gravity. Okay, so this is the equation we are going to work with. The first one, Euler, this is the gravity, and incompressible irrotational. And because the surface tension is 0 and we neglect the wind, there's no air density is 0. So the pressure is just 0 on the interface. Okay, and we know that it's well known that when surface tension is neglected, the motion can be subject to so-called Taylor instability. So the Taylor criteria basically requires that the negative dPdN to be strictly increasing inward in the fluid direction. Okay. So this P is pressure, N is a unit normal, it's outward unit normal. So minus dPdN is a gradient inward normal. Okay. So the pressure has to be increasing in the inward normal direction. And we know that if it's decreasing, right, that the force just rip open the fluid, okay, and there's an air bubble could form, then this formulation would be wrong, right? Because in this formulation, we assume that, say, initially the fluid domain is, say, there's only bounded by the free surface, and suddenly there's extra surface boundary appears in the interior, so the topology change, and this formulation has to be reformulated. So this is, or you can say that the situation is unstable. So you cannot solve it, okay? So this is, you cannot solve if this problem is violent, okay? But of course, I mean, this is a rough explanation. Okay, so this Taylor's condition criteria was formulated by G.I. Taylor in his paper in 1949, 50, or 1950. So essentially, he just looked at two simple situations, and he finds when the water is above air, and he calculates this, and it's pretty easy to calculate, and he finds this is always negative, so it's unstable situation. We know it's pretty clear if water is above air, it's unstable. If air is above water, it is stable. Okay? And he calculates negative dPdN possible stable. Okay, so now let's just review some result now, like it's already 17 years ago. Okay, so in fact, what we can prove, so in this is work about 17 years ago, what we can show is that actually the Taylor-Stein condition always holds, okay, as long as the interface is non-self-intersecting. So this means that even if wave, overturns like this, okay, and negative dpdn is always positive. Okay, so there's always, in fact, I purposely draw it like smooth. Okay, so if this curve, so this is what we proved like 17 years ago, is if the interface is C1, I write C2, but actually it's a little bit more than C1. Okay, and there's a lower bound, strictly positive lower bound. Okay, and this is then, as a consequence, we can solve the water wave equation for a short period of time. Say, so this is always true, and as a consequence, so for any given wave, initial wave that is, say, has finite many derivatives, and the velocity has finite many derivatives, and you can show that there's a unique solution exists for a finite period of time. That means the wave will stay as regular as this initial state for a short period of time.
Yeah,
Okay,
question.
Yeah.
Can you tell what C0 is in advance somehow, or are you just saying there exists one?
Yes, that's a good question. In fact, okay, we can tell what is C0. Yeah, actually, there's a formula we are going to use. So I'm going to give you a proof. Okay, so actually, I'm going to give you two proofs. So yeah, C0 can be determined. So here I have to make clear, right? It's because I mean, there's a lot of things I'm not mentioning. So I'm assuming that the at spatial infinite is infinite large domain. Okay, so acceleration tending to 0, velocity tending to 0 there. Okay, it's crucial because you can, otherwise you just move your frame up and down and it will break. So there is a reference there. Okay, so of course, I mean, if you think that this in fact should be always true, and you just go about to prove it, well, it's not easy, not difficult to prove. Okay, it's very easy to prove. So in fact, this proof is the second proof. Okay, so the second proof is you just apply divergence to both sides of the Euler equation. You apply divergence to both sides of the equation, then of course the first term disappears, and the second term, because curl equals 0, you calculate just gradient v squared, and that's equal to negative Laplace p. Okay, so you find Laplace p is less than or equal to 0. So this is like concave down, right? And we also know the pressure is 0 on interface. And now just taking into account the conditions at infinity, and you can show that actually just using a maximum principle, it's always greater than or equal to 0. And of course, we can do it precisely. That's greater than or equal to a constant just by a Green's identity argument. Okay, so the proof is very easy, but this is the second proof. So, but of course, I mean, this is Taylor's sign condition always holds, and I mean, for mathematician, we find we need to prove it, or we actually don't find it. Some of us may even think it may not be true, but in fact, this is true. And actually, yesterday, Steve showed us a video, right? A lot of video of surfing, right? So we know that the reason the reason you can surf is really because this wave is smooth in the tube, right? And it's stable, because otherwise you won't be able to surf. If it's splashed down, it's bubble everywhere inside, you're not going to be able to surf. So surfer knows it all the time, but we have to prove it. Okay? So of course, there's always, this is like redundance of mathematicians, like what you say. Okay. Oh yeah, but interrupt me at any time, okay? Because we're in this nice warm room, and if you have any remark or question.
So how would bottom topography?
Good question. Yeah. In fact, I have a formula. I derived a formula like maybe 15, 16 years ago, but I never published it. I just for my own enjoyment, I can show. But I cannot explain it anymore. I don't remember it. Because I was looking at some time ago, and I couldn't figure out. Because
Is the result still true with the Taylor sign condition always holds even for finite vector? It depends on the infinite.
No, it's not. So it's not always true, but for flat one it is. Okay. For flat bottom it is. Actually, say so if I remember it correctly, so actually this is it explains very well. This Taylor sign condition is saying is very good. So suppose you have a bottom like this. You just think about, no, it's not necessary here, right? So you just think about this is a big piece of rock. Okay, so if you have something like concave like this, okay, a piece of rock, and then you have a wave very close, and then you have large enough velocity here, you will see splash. Okay. This actually is negative deviation is negative here, okay, in this section. Okay. The formula, you can see from the formula that this is the case. So it explains that why we see some white water around the rocks, right? Okay, so it's actually quite relevant. Okay, even though
Well,
it's
that
mathematician.
may
Yeah.
may actually also give you negative dPdN on the free surface.
Yeah, it's negative dPdN on the free surface.
Yeah, on the free surface.
It is negative dPdN
That's right.
on
That's
the free
right.
surface.
That's why when waves break near reefs, right?
Yeah, near. That I don't know.
Well,
Okay, so yeah, if you have a rock like this, concave up, I remember looking at the formula, I got this conclusion, but for some reason I just never feel. Eventually, I just didn't publish it. Okay. And just keep it to
Sure, but
myself.
this would be interesting.
Huh?
This would be interesting.
So that means I should really just figure out my formula
Yeah.
again and publish it. Okay, I will try. I will try. Okay. Okay, so actually the formula used Riemann mapping to do that. And of course, this is the second proof. And the first proof used Riemann mapping, and it's purely mathematical. Okay, it's not as simple as this. This second proof is, the reason I did it is I did the first proof and I sent it to Cavendish and Tom Hall, and then they said, well, they say, well, actually the Taylor-Sum condition is really negative dPdN, because I was looking at the formulation of Tom Beer, Tom Hall, and the Rowan group. They somehow didn't mention negative dPdN as a sum. They wrote in a different form, so I just straight did a mathematical calculation and find it's positive. But the Cavendish suggested I look at this quantity, and then I actually came up with the second proof. So that's not the first proof give more information that we are going to use to understand the angled waves. Okay, so of course the motivation is for proving this is really contained in the earlier work, right? So in this work of Tom Beer, Tom Hall, Rowan group, and they show that if you have a wave that satisfies Taylor-Sum condition, and if you linearize about this solution, then the equation is linearly well posed. Okay, so the importance is already there. That's why we went to prove it, because I was in Northwestern University, and I look at the Michigan Lake, the wave overturn, I just feel it's always positive, so I proved it. Okay, otherwise. So it's really like you feel it is true, so the reason, if you go about prove it, it's not so difficult. Okay, so
Are you trying to say that deep inside you're an applied mathematician?
I'm always a mathematician, applied mathematician. I am applied mathematician. What do you mean deep inside?
Because you feel something is true.
Yeah, I
Right?
feel something is true, then you say you feel something is true, so you prove it. Because if you don't feel something is true, then you just assume it, right? So this is the earliest work on the time-dependent water wave problem. So for infinite depths, in the 2D case, if the data is small, so that means the wave is almost like this, okay? And you can solve it for a short period of time, small and smooth data. And Yoshihara is able to put the bottom here, okay? And he can also prove that you can solve it for a finite period of time. But let me emphasize that this depth has to be strictly positive, okay? It has a lower bound. It's the height, so that means there's no interaction between the interface and the bound. Okay. So in this finite depth case, there's no interaction between the interface and the bottom. Okay. So of course now we can prove also for 3D, and the idea is using Clifford algebra, Clifford analysis. Essentially, we had a good understanding using complex analysis in 2D. Then we try to translate the idea to 3D. And Clifford analysis give you a very natural tool to do that. So, but I'm not going to get into it. Okay, so recent work, this work has been generated in many directions. So now you can also add non-zero surface tension, okay? And you can also add a bottom. So again, this bottom has to be strictly away from the interface, okay? And you can also add a non-zero vorticity. But in all these cases, the Taylor sum condition doesn't hold automatically. So if you calculate, I mean, every ingredient is necessary to prove what I assumed earlier, okay? So then you have to assume it. So you assume this is true, then you can solve the equation for a short period of time, or that means if your wave is smooth initially and remains the same smoothness for a finite period of time. Okay. And now actually, in between then and now, there's also quite a bit of work on the global behavior of for small and smooth initial data. Okay. So we have results on almost global and the global well-posedness for data that's small and smooth. Okay. And for this water wave problem I mentioned earlier, for this infinite depths, no zero surface tension water wave problem, okay, in both 2 and 3D. So here are the list of the work. Okay. So we did it like, actually it's 2007, okay, so published 2009. So we first showed that for 2D water wave, we can solve it. So if the data is of size epsilon, then you can solve it to the time scale of like e to the 1 over epsilon. Okay, so this is so-called almost global well-posedness. And for 3D, we can, for data of size epsilon, if epsilon is small enough, you can solve for all time. T go is between 0 and infinity. And the solution remains small and smooth and actually decay with rate 1 over t in 3D and decay like 1 over square root t in 2D. Okay. So the main idea, as was already mentioned by Nate just a few minutes ago, that is that we find this quantity. So this quantity is really so if this is a free interface, right, you just project the height function into the space of holomorphic function in the air region. And if you look at this quantity, and in addition, you do a coordinate change. So that means you don't work on Lagrange, you don't work on Eulerian, you just look at this new coordinate system, and this quantity will satisfy this equation. Okay. So this is linear on the left-hand side, the right-hand side has no quadratic nonlinearity. Okay, so this means, then that means the water wave equation, when you look at the right quantity in the right coordinate system, it is more linear, and then you can solve for longer time. Okay, so that's the reason we can do it. If you're interested, I can tell you more in the summer school or in private. It's up to you, right? I believe this is new. Okay, even though I think so of course, I mean, people there are many other work say that, well, we don't need your transformation. Okay, so basically they come up with different proofs. So this is a German Masmoudi Shatta, and are able to use the space-time resonance method they created to show that. And for small and smooth initial data, for 3D water wave, you can solve it global in time, and furthermore, the wave scatters. Okay, so I just want to emphasize their data is different from my data. Okay, you can talk about small and smooth, but how small, how smooth, all matters, right? Okay, so what is assumed small? But I don't want to go to details. And this almost global well-posedness is generated by Al-Azhar Delors and independent Ionescu Pasateri recently to global as well. And the basic idea is they further understand the cubic nonlinearity, and they realize that the cubic nonlinearity doesn't cause any trouble. Okay, so
can I ask a simple question? So in 3D, what kind of space or what kind of smallness do you need to use to prevent initial data that, say, focuses to a point? Because you can have very small data.
That's true. That's true. So this you need to decay. You need the wave tending to 0 at infinity. That's crucial. Otherwise, you will not have the decay. Like you disperse, so the wave disperse out. Right. In 2D, you have one direction to disperse it out. So decay rate 1 over square root t. And in 3D, the dispersion, you have 2 directions to disperse.
So dispersion is better in 3D, right?
Yeah.
It decays things
so
faster,
you
but focusing is worse in 3D.
I'm not sure. Okay, depend on what kind of data you do.
Well,
right?
exactly. So that's
So,
what I'm
so,
asking.
so this data, I have to say that, I mean, I think it requires a lot. Okay, let me just say that. Okay, so it requires a lot. It requires a lot. A lot of quantity needs to be small and smooth. Okay, so certainly this is not really, I mean, global and it's done. Okay, it's not global. There's only just, I mean, there's a lot more work needs to be done for that. Okay, so and assumes a lot, but let me just quickly go through this because I only have 1 hour. Okay, so three. Yeah, they further understand cubic nonlinearity. So and then Hunter, Ephraim, Tataru, in these two work, first they come up with another proof for the same equation using modified energy methods. So again, a different proof. Okay, and then again they prove global and by further understanding this cubic nonlinearity. So I want to not go. So these are different methods involved. Okay, so now, of course, the question is what type of singularity is in the water wave, right? How do we understand singularity in the water wave? So there's not a lot of theoretical work concerning, not a lot of understandings about the singularities in the water wave. Okay, so this is, so in Al-Azhar, Burke, Zuri, so they are able to just try to push down the regularity required in the smoothness in the interface. Okay, basically they can show that if the interface, so in earlier work, it's required that like quite many derivatives. Like in my work, it's HS s bigger than equal to 4, so it's like C3 half, no 5 half, no s, so whatever, right? So it's bigger than that. Okay, so anyway, so because the purpose is not to prove low regularity, so they try to prove some low regularity result, and they're able to show that if the interface has C3 half derivative, C is continuous, C3 half plus a little bit derivative. So in fact, it's like H2 in Sobolev space. Okay, and then it's H2 plus a little bit, and they are able to say that if the interface is C3 half plus a little bit, then it remains C3 half plus a little bit for a short period of time. Okay, and for this work, and they now very recently they can lower even a little bit. So it's C3 half minus a little bit. Okay, it's further using Strickhart's estimate. Okay, they can minus a little bit. So anyway, so this is what we very often see in the ocean, right? You don't really see much about this in the river because in the river the surface tension is too important there, right? So here in the ocean, we quite often you go there, you see this wave, right? And you know that. So the question is, I mean, what are we talking about, right? What is this? Okay, how do we understand this kind of thing? So how do we understand this? So how do we understand this wave? Okay, so this wave, of course, I mean, and when I show this picture, well, so some people say, well, this is because of wind. But of course, we know that, I mean, wind causes wave, right? But the wave travels long distance, right? The wave in front of you can be just coming from a storm from far away and then travel long distance in front of you. What you are seeing probably when you see this better wave, you don't feel much wind. It may not be because of wind. Okay, so
There's wind here.
huh?
There's wind here.
I don't know.
You can see it.
Okay, you can see it.
Look
Okay.
at the surface.
Okay. This is the ripple. This is the surface tension.
Yes.
That's right. Okay. So
So you can't show this because you have ignored the surface tension.
no, because I took it from somebody from internet. I don't know how they.
But it's not appropriate. I wouldn't show because you see too many.
Anyway, so we know the wave can with wind, can without wind. Maybe this one has wind, but maybe sometimes certain wave doesn't have wind, right? And then it doesn't mean there's no wind, no wave, right? This is
No, that's.
yeah. So okay, so that's my point. It's definitely it's not no wind, no wave. Okay, that's good. Then we can continue. Okay. So because in my equation I have ignored the wind. So I just want to say that when we ignore the wind, when we look at this equation. So that means we have ignored vorticity, we have ignored surface tension, no wind. What kind of behavior we can derive from this equation, right? So this equation is responsible for what type of behavior, okay? Okay, so what are some typical singular behaviors? Okay, so where does it come from? How does it form, right? And what are some basic structures of the singularities? Okay, so of course we look at this picture, we say, well, I mean, why? So how do we understand that, right? So this first, of course, let me just say that, I mean, there's surface tension here seems like wrong, but still we see quite a bit angle here, right? So that means it's not even C1, this surface, okay? So it's not covered in here, right? It's not C3 half. So how do we describe this? Okay, so how do we understand that? So the first approach we try is thinking that maybe some self-similarity is responsible for the singularity. Okay, so let's just try self-similarity, because we know that we are in the open ocean and the beach is far away from us, the bottom is far away from us, and we see this, right? The wavelengths compared with this, the boundary effect can be neglected, and we are not having wind, no external force. So typical behavior should be self-similar. Okay, so is this really some self-similarity here? And from a mathematical point of view, PDE point of view, we also know that self-similar solutions are basic building blocks of solutions of the equation, like heat equation, right? Heat kernel self-similar. In the shock wave theory, the basic building block is, I mean, the self-similar solutions. Okay, so we just try to look for some self-similar solution. And when we look at this, we think, well, I mean, who is responsible for this? So we think about it. I mean, of course, I mean, there is a natural scaling there, the gravity, but this may not be due to gravity, right? If we have to stay with gravity, there's no story. You just go with scaling x, scale like t squared, okay? But we think this is really a lot of motion, right? Things are moving about its momentum, okay? So we think it should be velocity is in charge, or convection is in charge. So we just try to see that whether there's self-similar solution in the region where convection is in dominance. Okay, so that means we are going to look at in this scaling region that space variable z is scale like time, okay, or in this hyperbolic scale. Okay, so it's necessary to neglect surface tension, because surface tension, if there's a surface tension, there's a different scaling there. Okay, surface tension will come up with scaling. And you have to neglect gravity, because we think this is convection. It's not gravity, not surface tension. We just set them equal to 0. Okay, but we do want our wave satisfy Taylor-Sine condition, right? Remember, we know that this is the situation. It's stable. So if you want to see the wave, you have to make it positive. Okay, so there's no choice. So what we find is the following. So if there is a self-similar solution in that scaling region of the Euler equation with no gravity, no surface tension, it has to look like this. So it has to concave up on this side and go up, and then it turns by a degree certain phi, and then concave up again. Okay. And we also find that if there's such a wave, this angle, so the reason for the concavity is because we want negative dpdn is greater than equal to 0. Okay, so the stability criteria force the two sides to be concave up. Okay, and if we don't want the wave overturned many times, like, you know, infinite many times, we never see wave like this, right? Then your angle mu, this angle has to be less than 90 degrees, and the angle at infinity has to be greater than 90 degrees. Okay. So, but of course, this is a little bit troublesome, right? Because I'm from Ann Arbor, and I don't really see waves every day. And of course, I start to doubt about myself, because I only see wave. I have took a lot of photos of wave, and only standing on the beach, and I know the wave coming to me is concave up, but I always thought the wave behind me should look like this. Okay, so I mean, there cannot be a wave like that. So I didn't know there's such a thing, but fortunately, I was invited by some friends to San Francisco at that time.
White caps.
Huh?
White caps. They're called white caps.
I don't know. Okay.
Yeah.
So anyway, I saw the wave like this, so I came back and I proved it. Okay. This exists. And because otherwise you're not motivated. I mean, if you don't believe you are right, I mean, why do you want to work, right? I mean, you better just, do something else. Okay, so what we can find is a symmetric one. Okay, so this angle is less than 90 degrees, this is greater than 90 degrees, and the velocity is just pushing down. It's symmetrical, so pushing down like this, and we go up. And this is the wave profile. Okay, so this I show you the photo I took in San Diego. Okay, so we know that wave coming from far away, right, and washing towards shore, and then there's a wave reflect. And I was standing in this angle that I can see the side of the wave. So you can see that at this moment, the two waves get together and round, right, nice and smooth, and sharpens up, okay, and break. And okay, so sharpens up. And I was very happy to see when it sharpens up, it's concave up to, at least to my eye, it's on both sides. Okay, so I blow that and I try to convince you it is concave up on both sides. Do you think so? No. Okay.
I've seen many of those, yes.
Okay. So if you've seen many of those, then I should have talked with you earlier. But anyway, so
Was this in La Jolla?
this is La Jolla.
Yeah. Because I was
You have
in
been there.
January.
Yeah. But I visited the math department. I didn't visit the script institute. Okay. So anyway, so if you're not convinced, this is something I also download from internet. Both sides are concave up. Okay, and then of course once you go back to this photo we want to understand, look like concave up on both sides to me. So I mean the reason I'm showing all these photos is I want to say that okay, the self-similar solution we find is relevant, right? You see that a lot of it, and that's exactly shows that we have found something relevant. But of course this is not the proof, right? How do you know it's relevant? It's not related. It could be just not related. Okay, so you have to work. So still this question is open. How relevant are the self-similar solutions we find? Okay, so this is not a proof. Showing some photos is not proof, even though it's encouraging, right? But it's not a proof. So are they stable? How do we fit in the self-similar solution in this photo? In this picture we see. Okay, maybe not this picture, maybe some other picture that you know that what I mean, right? Angled waves. Okay. So are they stable? So because only the stable ones we can see, right? We cannot see the unstable ones. Okay. Okay, so now let's leave this problem for a moment, for the minute. Let's look at a different problem. So let's remember that I have emphasized that all the previous work about finite depth wave, there's always the bottom and the fluid never interact. Okay, so now we want to say that, but in the beach, we know that. In the beach, okay, so maybe I use a different example. Oh, can I write it? Yes, I cannot lift it. No, it's fixed. Oh, okay. Is this okay? So in the beach, we know in the beach we know that this is beach, right? This is beach. And of course, the wave comes in like this. This is a wave. And of course, the interface always interacts with the wave. Okay, so how do we understand this? Okay, so of course, this problem is not easy. Okay, so this problem is not easy. And let me just formulate the problem first. How am I going to pull that? Yeah, I need to be a prime mathematician. So we want to consider the interaction of the surface with the rigid boundary. Okay, so of course here the rigid boundary assumed it's completely rigid, perfect, smooth. Okay, so we have an Euler equation. So the condition on the boundary is v dot n equal to 0, right? So it's rigid boundary. Okay. So the graph as I draw that, and now of course the domain is now has free surface and has a fixed boundary. Okay, so it has 2 points, and the fixed boundary we call it upsilon, and this is omega sigma t, right? It's a free surface. Okay, but of course this problem can be hard, right? Because so even though I formulated this, I mean it's not clear. Say we know that fluid particle when it's on the boundary, stay on the boundary, but those on the bottom can go to the interface to bottom. I mean, there's all kinds of issues involved. If we just start with this, we don't even know where to focus. Okay, so let's just focus on a simple problem. So this simple problem is the following. So suppose I have just a rigid, perfectly smooth vertical wall, okay, and I have wave coming in. Okay. This is a wave. Okay, so this is a wave. And maybe it has an angle, maybe it has just 90 degrees. We don't know, right? So this is a. So instead of looking at this more complicated problem, let's just to be specific. Let's just try to see what kind of difficulty there could be if there's a fixed boundary. So we just fix a vertical wall. Okay, we look at the vertical wall and we look at the free domain. Let's say the free domain is on the left-hand side. So you have wave coming back and forth, coming back and forth, right? And this, of course, I mean, we know that this problem is equivalent to the one that it's if you do a Schwartz refraction. Right? It's equivalent, right? So if you just push the wave in out like this, right? So okay, these two problems are equivalent because
Is velocity 0 in the wall?
yeah, velocity is v dot n equal to 0. Okay, so that means if you have a vertical wall, v1 equal to 0 on the wall. Okay, there's no, it doesn't go this way. Okay, it can go up and down.
Okay.
Okay.
Can't you prove that the angle is 90 degrees in that case?
Actually, I'm going to prove the angle doesn't have to be 90 degrees.
Okay.
So I think I don't understand why you think angle has to be 90 degrees.
Julia, you
Huh?
cited paper of 3 authors about it.
I cite a paper.
There were papers claiming that it
Yes, there was some existence theory for
Alazar, Burke, and really?
Yes. They consider problem.
Very good,
finite
very
domain.
good, very good. They consider this doesn't mean this is only case works, right? It can be other, this is the only possibility.
But
It doesn't mean that somebody consider this is the only choice, right? And other choice doesn't
Yeah.
exist, okay? So I purposely draw this a non-90 degree angle, yeah?
Just you're removing the wall now.
Yeah, I mean,
Yeah.
so I draw a non-90
Yeah,
degree,
yeah, yeah.
I want to
But-
remove the wall.
But
There's a crest
With a
now.
normal wave, you will have velocity.
No, there's no, why? No,
Yes,
it's because,
or
no, the velocity is symmetric, it's going like this. Symmetric.
Standing wave.
No, it's not a standing wave, it's not a standing wave.
No.
What is a
So
standing
that
wave?
is
It's not a
propagating
standing
wave, so it can't be.
No, it's not a standing
yeah.
wave.
Yeah.
It's not a standing wave. It's
It's
no,
a
no, it's
propagating
just
wave.
symmetric. You see, it doesn't go. Of course,
Yeah,
so if this is a solution on the right hand side, you just do a Schwartz reflection, you get a solution on the whole
I
domain.
mean, there's no wave here, right? It's just flow near a wall.
Yeah, yeah.
No, there's a wave.
What
What do you mean, no wave?
I mean, a wave is nothing propagated.
Oh, you can make it propagate. You can add a velocity. Okay,
But then you have to move your wall.
yeah, you no, the move. You're right. You have to move my wall. So for the moment, it doesn't propagate. Okay, so but you have to. We have to deal with things one by one. Eventually, the stuff moves. Okay.
This is standing wave, yeah?
I don't know. It depends on what is.
One example of this is a
So
standing
anyway, this is a problem I gave to my student. Okay, so I mean, it has to be solvable.
It's not
It
propagating.
doesn't matter. Probably not. Let's say. Yeah, I agree. Okay, fine.
Yeah,
Just
so
any
it's standing
solution to
wave.
the
Fine.
equations, right?
No, I haven't finished. I haven't even started.
Yeah, but we know.
Okay, I have to rush. Yeah, what's the question? What was the question?
Is the gravity included in what you're
Oh yeah, there's a gravity. There's a gravity. No, there's a gravity. Oh yeah. Oh yeah, there's a gravity. No, definitely there's a gravity. Okay. So of course we have to start from somewhere, right? We start from somewhere. So my student Rafe Kinsey, he needs a thesis problem, and I say, well, this is a workable problem, right? You have a cup. You see, you have water here, and then you move. What kind of angle it can form with a boundary, right? I mean, that's a natural question. I mean, you just move it, and then you look at it. Does it have to be 90? So what if it's 90, right? So of course there are two possibilities. You see, this is let me just use this for Is there erasers? Oh. So let me just use this word. So of course there are two possibilities, and there's argument says, oh, let me just emphasize, in all the previous work, negative TBDN has to be greater than positive constant, right? That's Al-Azhar law, everybody. Okay. So no, and the Al-Azhar Burke's rule. Okay. So there's two possibilities. So of course, one is this is a wall, right? I try to remove it. The wave comes in 90 degrees. So once you reflect it, it becomes this, right? And it's smooth, perfectly smooth. So it's reduced to the earlier work. We already know smooth. If the interface smooth, there's nothing to do, right? If it's smooth, if it's 90 degree, it's just easy. You reduce to no work case, and it's smooth. I mean, we know about it. I rave. Of course, I say that, well, we should not work on this. Okay, so because there's nothing new. Because you cannot publish a paper on that, right? Because people will say we already know it. So the question is, this is a wall. So now, is it possible to form an angle that's not 90? Okay. Is it possible to have an angle that's not 90? Okay. So that's the question I asked him. Why I just tell Ray from the very beginning that we should now work on 90 degrees? Because he finds a difficulty. So the question is it possible for the angle between the interface and the wave to be other than 90 degrees? Okay, is this possible? Maybe it's not possible, maybe it's possible. So in fact, we study a little bit different, but anyway, that's the same thing, right? We want to just focus on one angle. So this is what we assume. So now we, instead of just one wall, we have two walls. So just have to have something to think about. We have a cup, right? Instead of infinite domain. Okay. So you have two walls. One is at x equals 0, one at x equals 1. We say that, okay, let's allow this angle to be 90. Okay. But this one, we want to say whether this is not 90. Is it possible to be not 90? So we reflect about this wall. Of course, we get no difficulty here, right? Because this is just 90 degree, and this is not 90, and then we get a symmetric domain. Okay, now we have a periodic case. So now, of course, you can extend it. You can extend it like periodically out, but of course, it's periodic in a singular domain. Okay, so can we do that? Okay. Okay. So the question we want to understand is really this can be other than 90. So we want to understand it from the well-posedness appointment. Okay, so a local existence. Say, suppose initially we have a wave like this. Can we solve the equation for a finite time? Okay, so we want to do some energy estimate. Okay, so let me just give you an answer quickly because my time's up. So the answer is yes. There is a local existence in this framework. In fact, in the process of dealing with just one angle, we can actually deal with many angles. Okay, so the angle doesn't have to be 1. That angle doesn't have to be 90. You can deal with arbitrary interface like that. Okay. As many angles as you want. Okay. Any angle surface. Interface can have any angle crest, and this angle doesn't have to be symmetric. You see the refraction is symmetric, but the one we solved actually doesn't have to be symmetric. You can have angle like that as well. You can have an angle like that as well. Okay. So okay. And it can overturn as well. Okay, so now what we learned from
Sorry, where is new and
new
on your drawing?
what?
On the blackboard indication. No, in the left bottom. Here, where? Here,
New. Oh, here it's a different angle, right? It will be.
Here, true new.
Okay. It depends on, but it doesn't have to be symmetric. Okay, so anyway. So what we find, angle mu, okay, the angle mu, this angle mu, the mu, this is the angle with the wall, has to be less than, okay, so let me just to be precise. From the equation, we learned that this water wave equation with no wind, no surface tension, no vorticity, tell us that you cannot have this angle to be greater than 90 degrees. So that means if this is your wall, your water never comes in like that. Okay. That makes sense, right? We always see, if you shake your cup, the wave, this is always less than 90 degrees, okay, here. And in fact, the water wave equation, you see that I'm drawing this. I think you probably have drawn it when you were a kid, right? So like this angle, inner angle is always less than pi. Or less than equal to pi.
If your cup had an inner cylinder, though, then and you showed it might.
Huh?
do the other.
What?
If you had a cylinder in the middle of your cup and the fluid was outside it and you spun it, I think it would go the other way.
But you keep spiral, no? No, but I showed. Oh no, this is 3D.
Because you're up
No,
against
I'm
the wall. Oh,
in
you're in
2D.
2D. Okay.
Okay. I actually didn't check 3D. Yeah, 3D it might be a different singularity. I don't know. Okay. So this is joint work with wave. Okay. So the equation tells us this angle has to be less than equal to pi, and that also makes sense, right? Because we never. I don't believe we have see a wave like this in the middle of the ocean. This angle greater than pi. Right. Never.
But can these be standing waves? Because with standing waves, you would get.
Standing wave doesn't go like that either.
Yeah, with standing wave,
Really?
you figure it goes like this, and then.
Oh.
this
So
It
we-
doesn't
like
form
this.
a crest at the
No,
bottom.
flat.
It's very flat.
Yeah, it's flat. You see, it doesn't form a crest. Maybe I proved your computation. It doesn't form a
It
crest.
doesn't form a crest.
Yeah, that's a standing wave. If it's a standing wave, you're right. I never thought about standing wave has to go like this, but for me, now of course this angle can be smooth, right? Can be pi, but less than equal to pi, but not greater than pi. Okay, so you cannot. So it probably just proved that it cannot be any angle in standing wave. Okay.
Let me ask, is this new assumed in the initial data? I mean, so you start like this and you have existence only for such angles, or you are looking at time evolution and...
Is this new?
No, I'm just asking for more details. I don't
Yeah,
understand.
it's new. Of course it's new. I tell you why it's new. Okay, so I haven't got to the point.
What is it about?
But why some people
he
say
doesn't mean new in the sense of new. He means new, the angle new.
oh.
New.
He says, do you assume new is less than 90? And
No,
then
no,
you
I don't know. No, I prove it's 90.
So is it?
I prove it. I prove it.
The initial
Yeah,
data,
no,
or-
I know. I proved the equation doesn't allow you to have greater than 90. Okay. So you see, that means that's a good equation. It's not too simple. Okay. This is equation captures some very typical behaviors. It's not because of the wind. We see the wave because it's a typical behavior. That's not, the angle crest doesn't have to be due to wind. That's what I want to conclude. Yeah. I only have 10 more minutes.
That we agree that when you have the vertical standing wall, take a microscope and look to the elevation, then it's 90 degrees. You agree with that? Always.
No, it's not. It's less than 90. You see, you
It's
know,
always
micro.
90 degrees.
No. I think there's one thing. You see, in reality, of course,
Then the vorticity.
no, in reality, of course, here's this.
No, I'm
When
not
you
talking
get,
about that. I'm
when
not
you,
talking about that. I'm talking about the standing wall.
So please,
The wall.
please let me
questions one at a
finish.
time.
Let me finish. No, so maybe I will discuss. Unless
Questions one at a time to the speaker.
unless
please,
you
otherwise it's very
don't feel
difficult.
too hot here.
may I maybe interject one thing?
I have
I think you're talking about physics. For her, the case of a wall and the case of a crest is exactly the same.
Yeah.
Okay?
Yeah.
So don't worry about it.
Yeah. Good question. So this is, I have to clarify something, right? So here, I think whenever I talk about war, some engineer people will start to worry. You see you have a triple point of interaction here. You have friction there. But you see here, we are neglect surface tension. Here. There's no friction here. So this is not contact angle problem. Okay, it's different.
No.
Yeah.
So then it's 90 degrees.
I don't know if it's 90. Okay, so anyway, let me show you.
Based on the prior estimates for elliptic equation with domain distortion.
No. Okay. I don't know nothing about elliptic equation. So I only know Euler equation. So let's see. Let me finish that. Okay. So the angle from the Euler equation tells us incompressible irrotation. The Euler equation tells us this angle cannot be more than pi over 2 at here, and here cannot be more than pi. Okay. Can I continue? Because unless can I Can I have extra time? I can answer your question if I have extra
Well,
time.
I'm not the boss, but you can continue.
You can continue.
Okay, you can leave if you don't feel.
The only constraint is
feel too-
pizza.
You have to eat.
The delivery man will eat the pizza, so that's okay.
And beer.
Just continue. No pizza, no beer. Continue.
Yeah, I think we asked them to deliver to here, right? So the angle, the interface. So this the second sentence I'm writing here. In fact, because I'm going to tell you the next thing. Okay, so I need it right now because the equation tells us you cannot. The equation tells us this is. You mean this is the phenomena we are seeing. I mean, we are seeing so often. This is really the Euler equation say that force us to be like that. Okay, it's less than pi and less than pi over 2 at the boundary because the reason you haven't seen because you never see because the equation doesn't allow it. Okay, so why is this? So the first difficulty, of course, so what is the difficulty, right? So I want to tell you what is the new, okay? So in fact, so this is what Rafe came in, like after 1 week, I gave him a problem. I mean, he's a smart guy. He said, well, Sijue, we're in trouble. Negative dpdn has to be 0 at the wall if the angle is not 90 degrees. Okay. You see, all the previous work rely on greater than a constant, right? A positive constant. Now it's equal to 0 at the wall. And he gave me a very simple argument. So this is really the difficulty. So it turns out we can, in our framework, we can still prove negative dpdn is always greater than equal to 0. But it's equal to 0 at the crest, at this point at the sharp crest and at the boundary. Okay, when it's not 90 degree, when it's not 90 degree. Okay. So let me just say one more sentence here. I'm neglecting bottom again, right? So because I mean bottom is really not a difficulty here. The real difficulty is the interaction with the wall. So we just forget about that because we want to focus on deal with this difficulty. Okay, so let me just tell you why the negative dpdn has to be 0 on the boundary. Okay, so let me just start with, this is actually the formulation I have been working on like since 17 years ago. Basically, you write the interface in Lagrangian coordinates, right? So alpha, this represents the particle path of the same particle. If you take derivative to t, you get velocity. To derivative, you get acceleration. And of course, gravity, we just normalize to be 1. So that's minus I is the gravity. So I use complex variable, 2D. And we know pressure is 0 on the interface. So that means gradient P has to point in the normal direction. And in the normal direction, we decompose gradient P in the tangential normal direction. So the tangential direction disappears. We only left with normal component. And normal component A is a real valued function. It's precisely this multiple times minus dpdn. Okay. Z alpha is tangential derivative, so Z alpha is points normal direction. Okay. Okay, so now we want to write the Euler equation on the interface. Okay, so divergence curve equals 0 implies V bar is holomorphic in the fluid region. And of course, the V dot n equal to 0 on the 2 sides implies that the velocity, on the 2 sides, so the 2 sides, on the 2 sides, the velocity are the same and are purely imaginary. Okay, so I mean these 2 sides. Okay. On these 2 sides, the velocity are the same and only moving up the down simultaneously. Okay, so yeah, so we know that. So this is because now we can use complex analysis, right? So we know that holomorphic function is characterized by the Cauchy integral. Okay, so Cauchy integral formula give us this characterization of the boundary value of a holomorphic function, periodic holomorphic function, because the periodicity coming from here. So this is characterized. I mean, this is really basic Cauchy integral, and the Nate has already defined it, and I'm not defining it because this is fully nonlinear ones hard to work with. We in fact want to use Riemann mapping. Okay, so let's just write down this. So this is the equation of the free surface, okay? But this is a fully nonlinear equation. We cannot solve it directly because we need to know what type of nature, right? Is it hyperbolic, elliptic, blah, 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 right? So it turns out, if you just take one more time derivative to the first equation, and you move half of there are two terms here. You move one of the terms to the left, and the left-hand side forms higher order terms. So what I'm talking about here is really the 1997 paper. Okay, it's not the new paper. This is a quasi-linear equation. Okay, this is a higher order term, and if I let u equal to zt bar, that's a velocity bar on the boundary. So if you take derivative to tangential direction, that's a tangential derivative, and you times I exactly is a normal derivative. So this is a dilution normal operator we are talking about all the time. But I now like to write dilution normal just like I d alpha, because I d alpha acting on a holomorphic function is really just the dilution normal operator. Okay, it's just convenient to use. We don't have to do this non-local stuff. Okay, so this is a classical case when the curve is smooth. Okay, when it's a smooth case, that's the equation, and we have proved. So we have proved A is this guy, right? We have proved when this curve is smooth, this is always positive. So you get a hyperbolic equation because gradient n is, we know, is a positive operator, right? And it's a non-negative operator because this is a dilution normal operator. It's like you just use the Green's identity. That's greater than or equal to 0. This is a positive operator, then A is positive, so this is a hyperbolic type. But now if A can be 0, then we're in trouble, right? So this is no left-hand side is not in dominance anymore, right? The right-hand side could be bigger because if this term disappears, there could be some important thing here, and then the nature could change. And I just say that, oh, it's degenerate hyperbolic. But at this point, it's not even degenerate hyperbolic. Okay, so this is like the trouble we got into, that A can be 0. So why A can be 0? This is argument of Rafe gave me after 1 week. He looked at this, he said, well, now that's the equation, okay? So this is a free surface equation, okay? So we know that free surface A is real, so that means you just write down this equation component-wisely. It's the right-hand side, so you write it. So that means ZTT plus I is perpendicular to Z alpha, and you write it down. It's exactly this equation, okay? And now if you calculate the angle, if this is mu, and it's very easy. Let me go quickly. So this is x alpha, y alpha, and you find tangential of mu is minus x alpha divided by y alpha, okay, and which equal to ytt plus I over xtt. But we know along the wall, the velocity is the fluid particles just move up down, right? So there's no tangential component, and there's no x component. Okay, so xt is always equal to 1 equal to 0 along the wall. So if you take derivative to t, of course, it's always equal to 0 along the wall. And this guy is always equal to 0 along the wall. If you want the angle to be not 90, this guy has to be not 0, right? If ytt plus I equal to 0, if ytt plus 1 is not 0, then this angle has to be 90, right? Okay, so that means if the angle is not 90, ytt plus 1 has to be 0. And remember, that's gradient p, so that means xct 0 on the wall, ytt plus 1 equal to 0 on the wall when the angle is not 90. So that means gradient p has to be 0 at this point. So, of course, what is the normal derivative? Normal derivative is m dot gradient p, right? Has to be 0 on the wall. So dpdn has to be 0. And we are in trouble. But I say, well, we have no choice, right? Because nobody will kill us if we work on 90 degrees. We have to see whether. So we continued anyway. So we continued. Okay. So I think you leave whenever you feel like. Okay. So let me continue. It's okay. I go slowly. Okay. So because I'm not very good when I have to rush. So, okay. So A equals 0 at the corner. So this is a single argument, right? Simple argument. Okay, so this is a case, that means that that's a situation we want to work with. We want to ask whether this can be, now here we come with argument at the boundary, it has to be no more than pi over 2, okay? This just comes from the equation. So why is that? So we use Riemann mapping. So again, let me just mention that Riemann mapping has been used in the 1997 paper. In fact, Riemann mapping is very useful because it captures the geometry of the interface and also it simplifies the matter, right? Remember that Cauchy integral, this guy is fully nonlinear, it's hard to deal with. And it's difficult to understand the structure if you don't use Riemann mapping. Okay, so Riemann, or in other words, I would say Riemann mapping allow us to go into very good understanding of the structure. Okay, and so let's see. So we use Riemann mapping. So we use the Riemann mapping. This is a reflected domain. So takes the Riemann mapping takes this point to this point, this point to this point, and infinity to infinity. Yes.
I just don't understand. When you said now the YTT plus 1 has to be 0. That just means the thing is in free fall, right?
That's right.
Okay.
Oh, yeah.
Okay.
No pressure.
Yeah.
It's just free fall.
Yeah.
Okay.
So in other words, it's going down.
Going down or going up? No, there's no gravity. No.
No, it can be going down.
It can go. Yeah. One is gravity.
But it's a
Yeah.
second derivative.
Yeah, YTT plus gravity
It's
equals 0.
It's in free fall up or down. It's
Yeah.
accelerating down.
So at the crest, if you have a sharp angle, grad P has to be 0. So in the same, I'm going to give you argument a little later that at this point in the interior, if you have a crest like this, it has to be 0. There also, okay. But actually, if you do have a crest like this, it's infinity. But you don't have upside down. Okay. So any other question? Okay. Okay. So that's so we use Riemann mapping. Riemann mapping allows us to flatten out the free boundary, right? And so as usual, we continue to a certain extent the framework is helpful in the previous work. Okay, so we just continue with the previous work, and I'm going to point out difficulty to you later. So of course, so we use of course now we restrict our Riemann mapping on the free surface. You get a mapping from this is a restriction. We call it H. Okay, so this guy is strictly increasing, right? You map this to here. Okay, so this is a change of coordinate we're going to use. So H inverse is just inverse in spatial variable, okay? And I just rewrite the interface in the Riemannian coordinates, Riemann mapping coordinate, okay? So it's like composed with H inverse, and also I take derivative. This is a notation, okay? So with a comma means I take derivative after I make Riemann mapping coordinate change. And this is a velocity field on the interface in the Riemann mapping variable, acceleration in the Riemann mapping variable. And the free surface now, this is the Euler equation. Euler equation in the Riemann mapping variable just look like similar. It's just notation change. Everything become in the Riemann mapping variable, right? You compose the H inverse, that's what you get. And then you have chain rule, you have actually H alpha. And what's a good thing is that so now your holomorphic function is in this domain, and that's a nice characterization, is in terms of this Hilbert transform. You see, this Hilbert transform is a linear one, and it's just so nice and simple. We can deal with it, and it's purely imaginary if f is real. Okay, that's the part we really like. Okay, so now this is still the old work. Okay, so now I'm going to show you what's the key ingredient of the first proof of negative dpdn is greater than a constant. Okay, and what's the difference here? So actually, the same proof applies to periodic case and also apply when there's an angle, but we will see the singularity very quickly just using this formula. So I'm not going to derive you this formula. I can probably do it in the last week in summer school if you are interested to see it. It's very simple to derive, actually. So because I was just so desperate to calculate negative dpdn, and I just came up with this argument in 1997. So this is the same argument. So in fact, I do have C0, a formula for C0 in the negative dpdn. Okay, so this is A1, and in that paper, and the same proof apply here. A1 is always greater than equal to 1. Okay, in fact, we can prove this is greater than equal to 1. Okay, has a lower bound, and there's a precise formula for that. I'm not writing down. So this is the Z alpha. Okay, and then we have. So now we can rewrite this equation, right? So now there's a comparison between 1 over Z alpha equal to acceleration divided by A1. Did I miss something? Okay. Oh, I missed something. Yeah, this is very important. Okay. So what is capital Z, right? So you see, I'm characterizing the free surface in Riemann mapping variable now. So what is Z? So Z, you see, this H is the Riemann mapping acting on Z. So capital Z is really little z composed with H inverse. It's exactly its Riemann mapping inverse. So this is the inverse Riemann mapping. It's a phi taking this from this flat to here. Okay. So Z inverse, capital Z is just this guy. So this is the boundary value of a holomorphic function, or it's really the boundary value of the Riemann mapping. Okay. Z is the boundary value of the Riemann mapping, and the derivative is that. Okay, so this is what we get. Okay, so this associates the Riemann mapping with the acceleration now. Okay, so now we can draw a few important conclusions just from this formula. Okay, it's strictly from the formula A is greater than or equal to 1. Okay, that was proved a long time ago. So from this formula, we can see that. So first, this angle has to be no more than power 2. Similar argument applies to interior crest as well. Okay, it doesn't have to be symmetric. So because you see that's phi inverse, right? So imagine you have to take Riemann mapping, you just put this angle at origin. Okay, so suppose this is at origin, this angle is at origin. And this phi inverse, the Riemann mapping have to take 90 degrees to mu. So this has to behave like a power law near this point, right? Near this angle. And this power law is exactly given by R, and R satisfy this, right? It takes this many R to open up a close pi over 2 to mu. Okay, so now you take derivative and you get this power law. Okay. So if this angle is greater than pi over 2, if this is greater than pi over 2, that means R is greater than 1. If R is greater than 1, so that means that the alpha derivative, this derivative has to be 0 at the corner. Now, if this derivative is 0 at the corner, that means this is infinity, right? And this is infinity, and we already know A1 is greater than or equal to 1, so that means acceleration has to be infinity. So now, depend on your perspective, right? Some of my colleagues don't believe that acceleration, he said that acceleration, of course, can be infinity. But some people say, well, acceleration cannot be infinity in physical situation. So if you believe acceleration cannot be infinity, then we are done, right? This angle cannot be greater than pi over 2. Because that's just a consequence of acceleration cannot be infinity. Okay, the angle has to be less than pi over 2. But if you are not satisfied with this argument, at the boundary we can actually prove it's always less than pi over 2. Okay, so why? Okay, so if you are not satisfied, so we know that this this has to be infinity, right? This has to be infinity, but we do know that xtt equal to 0 along this wall. Right, because this is just not long ago we said this, because xt equals 0, xtt equals 0 along the wall. Xtt equal to 0 along the wall, so in order for ztt equals 0, ytt has to be infinity because xct is already 0. Okay, so if ytt is infinity now, what is the angle formula? So that means this ratio has to be infinity, so again, the angle has to be power 2. So this angle can never be greater than power 2 without any assumption.
It can be equal.
Of course it can be equal. I mean, this is... we do see...
But she never claimed it could, right?
No, it's a smooth wave is equal pi over 2, but angled wave is what we care about.
But you haven't proved stability yet, so it could be that the only stable one is.
No.
But you haven't really proved existence yet.
No, yeah. That's my secret weapon. Okay, so let's see. I haven't finished. Okay, so now... So of course, here I'm just trying to cheat a little bit, but in reality, I mean, we just make life easier. We just say, well, we don't want Z. We want to work in the regime that acceleration is finite, okay? Because acceleration, I mean, if acceleration becomes infinity, you are out of the gravity wave regime, right? Because, I mean, gravity becomes irrelevant, okay? So if acceleration is finite, the interior angle cannot be over pi as well. Okay, so now y negative dpdn equal to 0 or greater than equal to 0. Okay, first. We can prove it's greater than equal to 0, and moreover, it's equal to 0 at these crests, these type of crest. Okay, why is that? So you see, you look at this formula. That's the formula, right? You look at this formula. This is gradient p, and you calculate this. This is like really just a normal multiplied by absolute value of z. And this formula just give you that negative dpdn is a1 over this, and which is greater than or equal to 0. That's how actually, so recall in that paper, our interface actually, I just assume C2, in fact, C1 plus a little bit enough. Then your Riemann mapping has no singularity, so that means derivative to z has lower and upper bound. So that means this guy has a lower bound and upper bound, so of course you would have a positive lower bound. Okay, that's how the positive lower bound come from. Okay, so it's a combination of A1 divided by the Riemann mapping. The Riemann mapping doesn't degenerate, then you have this. But of course, in the angle crest case, if mu is less than pi over 2, then 1 over z alpha tending to 0 at the corner, or tending to 0 at the crest if this angle is less than pi, then of course, if this guy 1 over z alpha tending to 0, then this has to be 0, right? So this is why negative dpdn is greater than or equal to 0 and equal to 0 on the crest, okay, on the sharp crest. So the energy. So I want to tell you what is the energy. Okay, so stability. Okay, so we can actually, I mean, a crucial step in proving existence is to prove a Pauli estimate. Okay, so that means you can find the energy, which is you take derivative, it is closed. Okay, the energy is closed in terms of time derivative. And turns out that, so this quantity, as usual, I mean, as an analyst, PDNist, we just take derivative, spatial derivative to the equation, but it doesn't work. Okay, so if you take straightforward taking derivative to this tangential direction, it's bad because it destroys the periodicity. And in periodic problem, you do want to integration by parts. I mean, if you have boundary terms like this, you have a delta function come up. It's not good. Okay, and also like, I mean, we also want to use some analytical tool also destroy. We cannot apply. So we have to find a quantity that's periodic. It turns out this is a good quantity. So what is this? This is actually a very natural one. This is just the, we know that we are looking at the, I mean, everything in this domain, the velocity field is periodic, right? You just imagine this is same here. So you just take derivative to the, this is holomorphic function. You take derivative to the spatial variable z, complex spatial variable z. You still get a holomorphic function, and it's periodic. Okay, so that means this is a periodic because complex analysis tells us that you take derivative to z to a holomorphic function, same as taking derivative to minus I dy. So that means if you take derivative to, I mean, two things moving up, down in the same way in the y direction, it still keeps the same behavior, right? Doesn't destroy, so it's still periodic. Turns out this is the right quantity to work with. And so that's our derivative we want to use, but the difficulty is we have a complex weight. And this weight is singular, right? Because it's equal to 0 at the crest, it's a sharp crest. Now we go back to, actually it's an abuse of the notation. We don't know at this point it's quasi-linear, right? Because A equal to 0 now, okay? But turns out we still can prove. The result, let me just say it quickly, is what we could prove is it's still quasi-linear, and these two terms still dominates, even if there's a sharp crest, is an angled crest, okay, not sharp crest. This angle doesn't become 0, okay? It's anything between 0 and a 90, and it's 0 and a pi over 2, pi, okay. Okay, so that's what we got. This is our quasi-linear, is the equation on the free surface. So we just take derivative to this, we get this equation. Now, a natural energy, this is a classical case we use. We just use this energy, okay? So when there's an angled crest, this doesn't work, okay? So in fact, this guy becomes infinity. You just plug in our quantity in there, it's infinity. We cannot use that, okay? So the idea is really use some weighted energy. So we weight like this, 1 over A, so remember this A is like dpdn H alpha, also similar like dpdn. So it's like, in 1 over the energy, we multiply by H alpha, 1 over the energy, we divide by H alpha. Roughly, it's you divide and a plus roughly inverse singular weights. Okay, and I don't go into detail.
But why don't you use just the Hamiltonian? You have, of course, derivatives.
I cannot prove with a Hamiltonian.
Yeah, but that's the energy.
No, no, it doesn't work. It doesn't work.
Yeah,
no, actually,
you
that's
get
a
delta
good
functions, but that's all right.
No, it doesn't work. Actually, you see. Actually, what's interesting with this energy, Hamiltonian is too rough. Okay,
Yeah,
it's
but
it's
your
too wrong.
basis,
No, no,
it's
it's
a starting
no,
point.
it's not my stuff. You cannot do that. Okay, it doesn't work. This won't work. Maybe you can show me a proof. Okay, but I
Yeah,
do this
but
one.
I
Okay,
would start as a physicist from the Hamiltonian.
you know, I can tell you actually,
Because you did that as
actually,
well.
I was in Paris last 1 month ago and giving this, as a hydrodynamic conference. There was a remark. Of course, I'm a very ignorant person. I don't know. There was a remark says that somebody say that for the Hamiltonian system, all the theorems are proved for using PD method. Never proved with Hamiltonian method. Okay. I don't know what it means, but I just repeat what other people said. Maybe I'm wrong. Okay. So
Just a
anyway,
comment,
yeah.
I guess the issue is that your energy is not a conserved quantity, but it's still useful for functional analysis.
Exactly. No, actually, this energy is very
Yeah,
useful.
but you can't call
If you in 1 or 2 months, I'm going to finish
It's
another
more.
paper. I will
It's
show you
more.
this energy is
Okay.
very useful, more useful than I'm talking here. Okay, but for the moment, I can only say that this is the energy we construct. Okay, so in fact, what we construct is not the very basic one. The basic one use only velocity field, like two derivative u square, right? Velocity square in the interior. That's too weak. Here you see we take one derivative velocity, we take two derivative velocity. We don't really have any reliance on the velocity itself. You see the velocity, everything has a derivative here. Okay, everything has a derivative in control.
But I can give you
We
one. But I can give you one immediately.
the derivatives
I can
in
give you one
control.
immediately.
The velocity potential
Much better. No,
is
no
not in
derivatives.
control. Okay.
Just potential energy. Eta squared.
Okay.
Because if I don't
No,
need
no,
conservation,
it's not
I
a
just
stronger
need
norm.
more.
This I haven't finished. Let me finish. Let me
Yeah.
Yeah, but I
because
know
your
the story.
energy will not tell you anything.
Oh,
Okay,
yes,
so
of course.
We can schedule your talk.
Yeah.
You prove the same thing with the Hamiltonian.
okay, so this is energy.
Tomorrow.
So this is energy. Okay, this is energy. Okay, so we do want the acceleration to be finite. So we put the acceleration here. Okay, so what we can prove is this energy is closed without any further argument, assumption. Okay, so this is, we take derivative to this energy, it's bounded by a universal polynomial of the same energy for a finite time. Okay, without any assumptions, further assumptions. And as a consequence, we can show that for any data satisfy finite energy, then there is a time so that we can solve it. This time only depends on the size of the energy, and we can solve it for a short time. Okay. So this is important, right? So what is really this energy? Let's try to understand it. Here it's too complicated, right? Two derivative, one derivative, and it looks like too mysterious. In fact, there's only time derivative here. So we try to understand this energy in terms of the spatial, the velocity field, initial velocity, and the position. Okay, in terms of velocity and position, that's what we get. So that means this energy is finite if and only if these quantities I'm writing down is finite. So this is L2 norm of one derivative of the velocity, and this two derivative of the weighted velocity, two weighted derivative of the velocity, and one derivative of the surface, 1 over z alpha. I never need to control z alpha. Actually, z alpha can blow up. Okay, and two weighted derivative of 1 over z alpha, and this is also again it's half derivative. Okay, half derivative L2 norm of 1 over z alpha times this. So this is like a special selection of quantity, and you have to control by itself. That's really the difficulty. The difficulty is really you have to close. You only involve these. Okay, so in classical case we could involve a lot more, but now the classical case, it's all become infinity. We cannot use. Okay, so let's make some remark. How do we come up with this energy? Okay, so first remark. So always in my earlier work, I always felt, the equations about velocity acceleration, right? And I don't really see interface. And eventually I have to state the theorem in terms of interface. I felt I always lost something, right? Because it doesn't translate. But in this framework, acceleration just is equivalent to 1 over z alpha, okay, in this relation. So any regularity requirement on velocity, acceleration, equivalent to give us the one on acceleration, 1 over z alpha. So in fact, in the energy, these terms doesn't appear. This term is like you just replace 1 over z alpha by ztt. That's in the original energy, but they are equivalent. Okay, so the second one is, well, so because we can solve it for a short time, right? So how did we come up with this energy? So in fact, we come up eventually what really give us the confidence that this energy work is that we plug in the self-similar solution. Okay, we find this has finite energy. And I say, well, self-similar solution, tells us a physics. Okay, if this works for the self-similar, we should be able to carry it out. So eventually carried it out. Okay, so self-similar solution has finite energy. Okay, and in general, of course, it's not just self-similar. So in general, you can plug in surface. It's rather complicated. You see, I never even specify any angle here. It's just these L2 norms, right? So, but of course, you want to see whether any angle is allowed. Okay, so you plug in, you find that you can have surfaces has angle crest with interior angle less than pi over 2. So the equation says that you cannot have the angle greater than pi. Okay, but your energy says that if your angle is less than pi over 2, it has finite energy. Okay, it cannot have greater than pi over 2. Okay, so and of course this angle has to be no more than pi over 4. So either two cases, either no more than pi over 4 or just 90 degrees. So here either pi over 2, no more than pi over 2 or 180 degrees. Okay, either smooth or that. Okay. Okay, so let me remark that I think we may have already forgotten about self-similar solution. That's exactly the angle allowed in the self-similar solution, right? So I mentioned that in self-similar solution, this angle has to be no more than pi over 2. So this is a set of, this energy is, we construct this energy and we can solve in this energy space. That means that you can perturb the self-similar solution, can still get a solution for a short time. So in some weak set, very, very weak sense, this self-similar solution is stable. But of course, stable has so many more meanings, layers of stability. So I don't want to claim this is the last answer, right? But at least this is some encouraging sign that self-similar solution could be relevant. Okay, so at least relevant in this case, it has helped us to find this energy, and also you can perturb it and you still get solution. Okay, nearby, and of course, this famous wave of Stokes of highest has 120 degrees will not have finite energy.
Call that 60 in your notation, though? Wouldn't you call that 60 in your notation?
Where did I have 60?
It's your nu is always half the angle, so shouldn't it be 60? Yeah. 120.
Oh, where is 120?
What's the angle?
So this has to be no more than pi over 2.
Well, no matter what, it's less than pi over 4.
Oh, sure.
So and then in Stokes wave, this angle is 120, right? 120 is how many? 2 pi over 3. It's too big.
Okay.
But
you can calculate, Longwood Higgins calculated the energy of...
But this is not the energy.
This is not energy. This is not energy.
No.
Okay, let me make one more remark before you talk. Okay. So let me make one more remark. So I have asked many people, right? Is this really worrisome? The Stokes wave doesn't have finite energy. I say no, it doesn't. It's not worrisome. Because
what is energy?
Huh?
What is the energy?
It's my energy.
But you can't see what it is. I can't see what it is.
That's okay. You don't see, I see. That's fine. I tell you what it is. But not yet. I haven't finished my last sentence. I haven't finished my pizza. So last sentence is I say, well, from what I can gather, I try to ask many people. Stokes wave of maximum height is considered unstable. So that means you won't be able to perturb it. So that's why the energy cannot be finite.
Do you know whether it's unstable or not?
Oh, people don't know? Okay, no, their results show
it.
it.
But it has finite energy.
It doesn't have my finite energy.
Yeah,
I
but,
cannot plug in Stokes wave and solve it.
let's not worry about it.
You can't call it energy. It's a norm, but it's not energy.
It's a norm, yeah. No, but
It's a norm.
mathematicians call that energy.
Oh, that's a mathematician. Abuse of language.
Yes.
Abuse of
Yeah,
language.
That's okay.
It's the Wu
No.
It's not a norm.
It's a norm.
Okay.
Yeah, you know, it's just a norm.
We
It's a function.
wrap up the
It's
talks,
not-
thank our speakers, take the questions over to pizza.
Yep.
Sorry for take up so much time.
Thanks, Sijue, also for the patience.